This video is about an existence and uniqueness theorem for first-order IVPs. So that is a first-order differential equation combined with an initial condition. One of the most important questions that we can ask ourselves whenever we're faced with an IVP is, first of all, does a solution exist? So should I even waste my time looking for a solution? Is there a solution out there? And then once we know that a solution exists, we often want to know if it's unique. If we're looking for a solution that describes a particular physical phenomenon and we find it, we'd like to know that that's the solution. That's the one solution that actually describes what's going on physically. And it turns out if that is not a unique solution, there might be another solution out there that is truly the one we're looking for. So this theorem is going to allow us to determine whether or not we have a unique solution to a particular IVP. So this video is going to be about the theorem itself. First, I'm going to explain it to you, and then we'll talk about what it means. And then we will discuss and outline some topics that you may need to review in order to apply the theorem. There's a little bit of Calculus 3 in this. I know many students take Calculus 2, then differential equations. So you might have to pick up some Calculus 3 skills pretty quickly in order to solve these existence and uniqueness problems. And then lastly, we will look at applying the theorem and some examples. So here's one version of the statement of the theorem. There are variations on this, but they all basically say the same thing. In all of the different textbooks that I've looked this theorem up in, they say the same thing in slightly different ways. So here's one way. It says, consider the IVP. We've got the derivative of y with respect to x is some function of x and y of x naught equals y naught. Now remember, f of x and y is a known function, and x naught and y naught are known values. Now this says if f, that's the function on the right-hand side, and the partial of f with respect to y are continuous on a rectangle R, which consists of all the points x, y in the xy plane, such that x is in this interval and y is in this interval. Oops, that should not be a B, it should be a D. Sorry. And x naught, y naught is a point inside R, so not on the boundary, but on the interior. Then we're guaranteed that a unique solution to the IVP exists on some interval, and we're not sure how large that interval is, but it's an interval that contains x naught, and that interval lies inside that larger interval that gives us the boundaries of that rectangle R. And of course, I'm adding and subtracting this h here, and we're assuming h is a positive number. So just a little bit more on this. Let's visualize what's going on. It says we've got a rectangle R, and it consists of this region. X is between A and B, and Y is between C and D. And x naught, y naught, it's very important. That is the xy pair associated with this initial condition. It's on the interior of this region R. So that's our region. We're told that if this function of two variables, which is typically represented as a surface in Calculus 3, z equals f of xy, right? If this function of two variables is continuous and it's partial with respect to y, that's another function of two variables. It's also continuous on this rectangle, and x naught, y naught is on the interior of the rectangle, then we're guaranteed that there is a unique solution to this differential equation that satisfies this. And remember what this means. This means our solution curve passes through the point x naught, y naught. So we're guaranteed a unique solution that passes through that point on some interval. centered at x naught, and we add and subtract h. So if this is x naught, then we'll subtract a little bit, and we'll add a little bit. And that h can be very small. So what we're guaranteed is that there's a solution that looks like this. And it could be tiny. It could be very tiny. It could be a very, very small interval where we have that unique solution, but we do. Okay. Now, in order to use this theorem, basically there are a couple of things you have to check. You need to check that f and the partial of f with respect to y are continuous on some open rectangle. And that open rectangle has to contain x naught, y naught. Now, often in these problems, we're not given x naught, y naught. We're just given the differential equation, and we're trying to find out where will we have a unique solution. What regions, or if x naught, y naught was in, what space in the xy plane, or what region in the xy plane would the IVP, the whole thing, have a unique solution. So yeah, we have to check that these two functions are continuous. So we need to remember something about continuity of functions of two variables. You'll also have to remember how to take a partial derivative of a function of two variables. It's actually pretty simple. I'll show you how to do that in just a moment. Okay, so let's actually apply this to a problem or two. This is one wording that you might see. So let's say someone asks you to indicate the regions of the xy plane where the conditions of the theorem above are satisfied. And then you're asked to sketch the region in the xy plane. And we're given this differential equation. Just for our first example, we'll do this. Now right away, notice that we already have dy dx by itself. So if I want to solve this problem, the first thing I need to do is identify f of xy. I would normally have to get dy dx by itself. It already is. Function on the right-hand side is f of xy. Now we want to think about where that function is continuous. So you always start this way. Okay, now for continuity, you really just have to remember those rules that you used to find domain in pre-calculus. If you're given a function that's defined by a single equation using those algebraic and transcendental functions that you're familiar with from all of your courses thus far, you really just have to think about where this function is not well defined. The functions that are defined this way are basically defined on their domains, so you just need to figure out the domain of this function. Now, when you're determining the domain of a function of n variables, and it's given by a single equation with those known functions that we're familiar with, there are basically three things that you have to rule out. We never want to divide by 0. We never want to take square roots or even roots of negative numbers, because that would give us a complex answer. We're not looking for that. We're looking at real valued functions here. And we can't take the log of a negative number or 0. This doesn't involve division, so we don't have to worry about dividing by 0. We don't have any square roots, so we don't have to worry about even roots of negative numbers. We don't have any even roots, but we do have a logarithm. So this function will be well defined when the expression inside the logarithm is positive, because you can't take the log of a negative number or 0. So we just take the expression inside. You set that greater than 0 because it has to be positive. That's going to be a log of a positive number in order for this to be well defined. And then you just take this inequality and you solve it for y. Typically, I can add y to both sides. And I get this. So x squared plus 3 is greater than y, or if you want, you can write it the other way. Y is less than x squared plus 3. Now, I don't want to write it this way. The region R where this function is well defined is the set of all x, y pairs such that y is less than x squared plus 3. So let's sketch it now. We know y equals x squared plus 3 is a parabola. It is shifted up 3 units. That's what that plus 3 does. And since this says y is strictly less than that, the parabola itself is not in the domain of this function. When y is equal to x squared plus 3, we'd have natural log of 0, which we can't do. Yeah, the parabola is a boundary of the region where this function is well defined. So we're going to just sketch it with a dotted line. Okay. And this function is continuous when y is less than this parabola. I think we all know that y would be greater than this value above, and then y would be less than the values given by x squared plus 3 below. But in general, if you're not sure if you should be shading this region or this region, just pick a test point. If the origin is not on your curve, not on that boundary curve, the origin is a really easy one to test. You just replace x and y with 0. So to test it, we just substitute 0, 0 into this inequality. And you don't always get a true statement. You substitute, you simplify, and then you look at it and you say to yourself, is that true? Is 0 less than 3? So that's true. So that implies that we should shade the side that contains our test point. So that's all of this over here. And if you're wondering to yourself, what exactly is that? That is the domain of this function. If you haven't taken Calculus 3 yet, I'll let your Calculus 3 teacher get more into this with you. But basically, the domain of a function of 2 variables is a subset of 2-dimensional space. If z is f of x, y, this is actually a surface. We can think of it like this. It's some surface that is up here above some region in the xy plane. Well, when we calculated the domain of that, when we computed the domain of that, what we were saying is that the z values are going to be well defined as long as we're in this region over here. So we're going to have a problem. Not really a problem, but that function will be undefined over here. But everywhere else, there's a corresponding z value. And we know that as this expression inside the logarithm approaches 0, we get natural log of a tiny positive number is a very large negative number. So the z values are going to negative infinity along this curve. They're approaching negative infinity. And then as they get farther away from this curve, it's going to increase the way a logarithmic function would increase. Still really hard to draw, but basically you're going to have some surface up here where that works that way. This is not what this surface looks like, but that's the idea. Okay, so we've got our function of 2 variables. We identify f, and we determine the region in the xy plane where it is continuous, we have. And the other part of this theorem says we need the partial of f with respect to y to also be continuous. So we need to compute that partial. Now, if you haven't had Calc 3 yet, that's okay. We can catch you up. The partial of f with respect to y it's called a partial derivative. It's basically the slope of this surface, this cartoon surface that I've drawn over here, in the y direction when you treat x as a constant. So if this is the x direction coming out at us and the y direction is going off to the right, this is going to give us a formula for the slope in that direction. And then all you do in practice when taking a partial derivative is exactly what you would think. If you're treating x as a constant and you're seeing what the slope is in that direction, you do the same thing in the computation. You treat x as a constant and you take the derivative of this expression with respect to y. So I've got natural log of a function. This is my inside function. Since I've got a function nested inside another function, I need to use the chain rule. According to the chain rule from Calculus 1, we take the derivative of the outside function first. The derivative of natural log of a function is 1 over that function. So we have the derivative of the outside evaluated at the inside, so you put it back in, and then you multiply by the derivative of the inside. Now this derivative is not 2x minus 1. When you're taking this derivative, you treat x as a constant and y as your variable. So you just treat this like a 2 squared or a 16 squared. It's just a constant as far as you're concerned. And the derivative of a constant is 0. The derivative of negative y with respect to y is negative 1, and the derivative of a constant 3 is 0. So this piece is negative 1. So I've got this fraction times negative 1. So I've got that right there. And remember what our theorem says. Our theorem says that this function has to be continuous and this function has to be continuous. Well, this function is continuous as long as that denominator is not 0. Because remember, when you're thinking about continuity, you're really thinking about domain issues. We need this function to be well defined. So we can't divide by 0. We can't take the logarithm of a negative number or 0. And we can't take even roots of negative numbers, not if we want real numbers out. There are no logs here, there are no roots here, so the only thing that we might get into trouble with is dividing by 0. So to find the region in the xy plane where this function is continuous, you just set this expression to be not equal to 0 and you solve for y. So we have x squared plus 3 is not equal to y. And actually that's consistent with what we had up here. If x squared plus 3 was equal to y, we'd be taking the natural log of 0, which is not allowed. Okay, so this is the domain of this function, and the domain and the region in the xy plane where this function is continuous are the same thing. So that's true. And then this also has to be satisfied, and it already is. So it looks like this is our region. So let's write down what we did. We computed the partial of f with respect to y, and then we determined the region in the xy plane, region or regions in the plane where the partial of f with respect to y is continuous. And the partial of f with respect to y is continuous everywhere except on this parabola. If I were to sketch it, we can't include the parabola, but we can include everything else. Now this region that I've sketched would be described this way: the set of all xy such that y is not equal to x squared plus 3. And this region over here would be described this way. I'll call this one, excuse me, r sub 2, and I'll call this one r sub 1. This is the set of all xy pairs such that y is less than x squared plus 3. Okay, so we need these to both be true at the same time. So we need xy pairs that belong to this set and belong to this set. And these xy pairs belong to both sets. So this is the region that we're looking for. And if you're still a little bit shaky about why that's true, let's go back to the theorem and make sure we understand it. The theorem says, given this IVP, if f and its partial with respect to y are continuous on some rectangle, and x naught y naught is inside the rectangle, then there is a unique solution to the IVP on some interval that looks like this. It's just a tiny interval around x naught. Okay, so really, I mean, all of these details about the rectangle and the interval, they're important, but in practice, I'm really focused right here. I need this function and its partial with respect to y to be continuous at the same time. And this function and its partial with respect to y, which we computed, are continuous at the same time on this region. It says indicate the regions of the xy plane where the conditions of the theorem are satisfied, and then sketch the region. So this would be our final answer. And again, what that means is if x naught y naught is any point down here, we're guaranteed a unique solution. If x naught y naught is on the boundary, well, actually we're going to have a problem because the derivative wouldn't be well defined there. If x naught y naught is over here, we're going to have a problem because we'd be taking the log of a negative number. But it turns out that this time we're guaranteed a unique solution as long as x naught y naught is one of these points out here, or any point in the region where y is less than x squared plus 3. Okay, let's do one more example. Same question, we want to find the regions in the xy plane, region or regions in the xy plane, where the IVP would have a unique solution, and we're just given the differential equation. This time I've got x squared minus 4y squared times dy dx equals the square root of x squared plus y squared minus 9. Okay, now notice how this IVP is set up. Dy dx is by itself, f of xy is on the other side. So we need to do a little algebra first, and we need to get dy dx by itself. Once we do, that function on the right-hand side is your f of xy. Now we need to determine where that function is continuous. Now remember, continuity issues are going to be the same as domain issues when you're talking about functions of two variables defined by those functions that we've already discussed in our previous classes. So we don't want to divide by 0, we don't want to take even roots of negative numbers, and we don't want to take logs of negative numbers or 0. So first of all, I noticed that I've got an expression involving x or y, actually both, in the denominator here. So this expression can't be 0, and I've got a radical. And it's not just a radical, it's an even root, it's a square root. So that means this expression under the radical can't be negative. It's okay to take the square root of 0. It's not okay to take the square root of a negative number though. So we need to find the region in the xy plane where this expression is positive and this one is non-zero at the same time. So the region R, where f of xy is continuous, is going to be the set of all xy pairs such that x squared plus y squared minus 9, that expression under the radical, is not strictly, it's greater than or equal to 0. And at the same time, simultaneously, that denominator cannot be 0. Now this is the region where this function is continuous, but I wouldn't leave it this way. We've got to do a little bit of algebra so that we can actually see kind of what's going on here. So let's take this inequality first and rearrange it. X squared plus y squared is minus 9 is greater than or equal to 0 is equivalent to this equation, or excuse me, this inequality. Add 9 to both sides and you get x squared plus y squared is greater than 9. So what does that mean? You guys remember what x squared plus y squared equals 9 looks like? I hope you said it's a circle of radius 3 centered at the origin. If you did, you're right. If not, you may need to go back and review that. This is not to scale. It's not looking very circular, is it? Okay, so x squared plus y squared equals 9 is right here, and x squared plus y squared is greater than 9 is either outside the circle or inside the circle. This circle is separating the plane into 3 different groups. It's the group or set of points where x squared plus y squared is greater than 9, the set of points where x squared plus y squared is equal to 9, those are the points on the circle itself, and then there's a set of points where x squared plus y squared is less than 9. You just have to figure out which one it is. It turns out that x squared plus y squared is greater than 9 out here, but if you want to check, just choose a test point. You can choose any test point you want, just make sure it's not on the boundary of the circle. I'm going to choose 0, 0 because it's always the easiest to test. So what you do is you plug 0, 0 into this inequality, simplify, and then you look at the inequality and you see if it's true. Is 0 greater than or equal to 9? Say, nope, that's false. Therefore, you're not going to shade the region containing 0, 0. You're going to shade the other region. So you want to shade the region that does not contain the test point when that inequality turns out to be false. So x squared plus y squared is greater than 9 out here. Now, if this was all we needed for the domain of this function, we would be done, but we're not done. We also have this, x squared minus 4y squared can't be 0. Now that's a difference of squares. You can think of that as x squared minus the quantity 2y squared. That can't be 0. And remember how differences of squares factor. A squared minus b squared can be factored as a plus b times a minus b. So what this is saying is that x is playing the role of a and 2y is playing the role of b. You get an x here and an x here, and then we're going to add and subtract just like you have an a plus b and an a, should be minus b, sorry about that, an a minus b over here, and you're going to add 2y and subtract 2y. So that's what goes there. If this times this is not equal to 0, that means neither of these are 0. So x plus 2y is not equal to 0, and x minus 2y, excuse me, is not equal to 0. And if you want to solve those for y, you can. So we have y is not equal to, subtract x from both sides, divide by 2, negative 1/2 x, and y is not equal to positive 1/2 x. Okay, so those are lines that pass through the origin, and they either have a slope of negative 1/2 or a slope of positive 1/2. So I'll do y equals 1/2 x first. We go through the origin, go up 1 and over 2, up 1 and over 2, and so on. And then you want to draw a dotted line through that. And then that's this line. Y plus is not equal to 1/2 x, because if it were, we would be dividing by 0. And then y is not equal to negative 1/2 x. So go down 1 and over 2 from the origin. And I'm using the origin because And when x is 0, y is 0 on both of those lines. The y-intercept is 0 for both of those. So this region that I've shaded, which is all of this out here, except for that line and that line, that is where f of x, y, excuse me, this function here is continuous. So again, we start by determining the region. Where f is continuous, and that basically comes down to your domain rules from pre-calculus. We don't want to divide by 0, we don't want to take even roots of negative numbers, and we don't want to take the log of a negative number or 0, and then we sketch the corresponding inequalities, or yeah, they're all inequalities basically, in the xy plane. And what that means is that this function is going to be continuous and well-defined everywhere except for these lines and on the interior of that circle. Okay, for our theorem, we also need the partial of f with respect to y to be continuous. So let's compute that. This one's actually a little bit more involved. It's a good opportunity to practice our derivative rules and our partial derivative rules. Instead of the square root, I'm going to rewrite that numerator as x squared plus y squared minus 9 to the positive 1/2 power. All right, so we've got the derivative of a quotient. So I'm going to use the quotient rule from Calculus 1. It doesn't change when you're taking partial derivatives. The only difference is you treat the other variable like a constant. So in this case, we're going to treat the x's like constants. The mnemonic is low d high, so you take the bottom function first and multiply by the derivative of the top function with respect to y, treating x as a constant. So that's low d high minus high d low. And actually that one's one I could do myself. I'll just do that right now rather than writing the derivative in up here. The derivative or the partial derivative of this with respect to y is the derivative of x squared, which is 0 with respect to y, minus the derivative of 4y squared with respect to y, which is a negative 8y. That's low d high minus high d low over low low, bottom function squared. Okay, now I look at this, I see I still have some more work to do. I need to compute this derivative. And here, what I have is a function nested inside another function. All of that is inside that those parentheses. It's being raised to the 1/2 power. So I'm going to have to use the chain rule for that. So the x squared minus 4y squared there. And then I want to take the derivative of a function to the 1/2. The derivative of a function to the 1/2 is the derivative of the outside first. So 1/2 of that function to the negative 1/2. So derivative of the outside evaluated at the inside. So make sure you put that inside function back in. Times the derivative of the inside with respect to y, treating x as a constant by the chain rule. And this turns out to be, well, derivative of x squared is 0 because there are no y's in it. The derivative of a constant with respect to y is 0. Derivative of y squared with respect to y is 2y, and the derivative of negative 9 is 0. So I've got low d high minus high times d low. That negative times the negative will make that a positive. So I'll bring that 8y out front. Oops, I forgot to square that denominator over low, low, bottom function squared. Okay, the 1/2 times the 2 gives us a 1. This is actually a fraction within a fraction. That negative 1/2 power means we're taking the square root of this, but we're taking the square root of that in the denominator. So this can be rewritten this way. I know you may be tempted to cancel this with one of these. Don't. It's not legal. If you're curious about why, please ask. Be happy to help you review why that's not a legal algebraic operation. So I've got this is in the denominator, oops, and I've got a y up here. And then over here, I have 8y, and that is another square root of x squared plus y squared minus 9. So now you've got a fraction within a fraction. And if you want to clear the complex fractions, and we usually do, we'll just multiply by that denominator. So we're going to multiply everything in the numerator and denominator by the square root of x squared plus y squared minus 9. If you want, you can go ahead and multiply every expression by that. Or you can write it on the outside like I did and then think of it as distributing. When you distribute this times this, those are going to cancel, and you're just going to get that numerator. And then over here, when you distribute, the square root times the square root is just going to give you that expression under the square root. But all of it's multiplying 8y, so you want to make sure to keep those parentheses there. Okay, so we did a lot of computation. Got to practice some calculus 1, and now we're looking at this and reviewing. So I've got the partial of f with respect to y, and I need this to be continuous. It's a fraction. It's almost a rational function. The only thing that doesn't make it, or makes it not a rational function, is that square root. But the same rules apply. We can't take even roots of negative numbers. We cannot divide by 0. We can't take logs of negative numbers or 0. Well, so this function, which is the partial of f with respect to y, will be undefined whenever this is 0. And it will be undefined whenever this expression under the square root, or it will be well-defined, excuse me, when the expression under the square root is positive. But now the expression under the square root can't be 0 because it's in the denominator. And if it's in the denominator, we'd be dividing by 0 if we had the square root of 0, which is 0 down there. Okay, so this function is actually going to be well-defined on a very similar region to where this one was well-defined. Our region will include x squared minus y squared, or include the condition that x squared minus 4y squared is not equal to 0 because of this. And then it will include this same condition, almost, except instead of a greater than or equal to sign, it's just going to have a greater than sign. So the solution to this problem, when they ask you to determine the largest region in the xy plane, where the conditions of the existence and uniqueness theorem apply, is going to be a region that looks like this, but it's not going to include that circle, because on that circle we'd be dividing by 0 over here. So let's answer the question. The largest region for which the conditions of the theorem are satisfied is this region. It's a set of all xy pairs such that x squared minus 4y squared is not equal to 0. And at the same time, x squared plus 4y squared minus 9, that's the expression under the radical, is strictly positive. We can take the square root of 0, but not if it's in the denominator, because then we'd be dividing by 0. If we do the algebra, and we already have, we find from this that y is not equal to plus or minus 1/2 x. So those are two lines that pass through the origins with slope of 1/2 and negative 1/2. And over here, we've got that region beyond the circle of radius 3 centered at the origin, not including the circle itself. Now, if you're saying it's not a rectangle, is the theorem really satisfied? Well, yeah, just put a little rectangle around any point. So we've got a circle of radius 3 here. It's not included. And I'm just going to draw a couple of lines. I'm not going to be as precise this time. That's y equals 1/2 x. And we'll call this one y equals -1/2 x. And the region is out here. Okay, so that's existence and uniqueness.